Hey everyone, and welcome to part 4 on my series on physics-informed neural networks. In this video, I'll be teaching you how to calculate the residual laws and the IC laws in physics-informed neural networks. So first, we can start off by calculating the residual laws. So we can define a function called PD underscore residual. Yeah, that sounds like a good name. And in this function, we're going to pass the model parameter z, xi, and the device which we're going to put the model on. So here z will be the coordinates n comma 1 and xi can be the damping ratio, which is n comma 1 dimensions. So first we'll define the z tensor. So we can define this as torch dot tensor z comma d type. Oh good, it's automatically filled. Here we use the data type as float32 and we're differentiating with respect to z, so it does require a gradient as shown here, and we put the device as device. So similarly we do it for the xi tensor. So we can go to the next line. So here we take the input tensor, the first input in the neural network. So input tensor is equal to torch dot concat. So we'll do cat. We can name this as, we can concat the z tensor and the xi tensor, xi underscore tensor, and let the dimensions equal 1. Yeah. Add an extra. So yes, that will be the input tensor, and now we can do the x prediction values. X pred equals model input underscore tensor. So this will be the x prediction values. We will instantiate the model later on the main training function. So we have the x predictions. Now to satisfy this differential equation as highlighted, we have to first calculate dx underscore dz. So it's going to be dx over dz is equal to torch dot autograd dot gradient x pred z tensor. Okay, so it's already been given here, so you can just, here what basically happens is that the x is being differentiated with respect to z, and we already have the x values as shown here. So similarly we have the first order differential, so now we calculate the second order differential. So we can do d square x underscore dz square is equal to torch dot autograd. Okay, so they've already auto-filled it here. What this basically does is finds the second order differential of x with respect to z. So now we have the PD residual, which is, we can calculate residual is equal to, yeah, it's auto-filled here as this, which satisfies this differential equation of the oscillator, and we can calculate the loss function using this. So loss is equal to torch dot mean. Here we're calculating the mean square error, so we use residual into 2, return loss. So this is the loss function. I had a mistake here. So this is how we find the residual function. Now we're going to calculate the initial condition losses, that is the boundary conditions that we have given in the initial problem. So here we can define an initial condition loss. So we pass in model, we pass in z0, which is the initial condition, z0, x of 0, v0, and the device which we're gonna put this on. So z underscore tensor is equal to torch dot tensor. Okay, I've already given the autofill here, which I've already explained. This will all be converted into a tensor data type with float 32. So now we have the z0 tensor and the z0 tensor. So we can calculate the input not is equal to torch dot cat. So this would be z0 tensor underscore tensor. It has an autofill, but okay. z0 underscore tensor, and this will have the dimensions equal to 1. Yes. So the x0 predictions, so we have to create the x0 prediction. X0 is equal to model of input 0. So this will be passed inside the model, this input 0 variable, and we get the v0 predictions as, no, we don't need v0 for now. Here we have to find the initial differential. So we do this is equal to torch dot autograd. Yes. So this is the first differential for the initial conditions. So now what we can do is get the loss underscore initial conditions equal to x naught pred minus x naught into, yes, this is correct, and we return the loss conditions average of the loss conditions. So this is how we calculate the loss conditions using the initial condition and the residual. In the next video, we'll be teaching you how to implement the training function of the model. Thank you.